Hi class, my name is Mwila Nyorongo and you're listening to Applications Development Software Specifications. We're going to be discussing a topic that is absolutely central to software engineering at scale. If you want to work effectively on a team, you need to understand the interface contract. Let's start with our usual high-level goals, the big three. We want our software to be safe from bugs, meaning it's correct today and stays that way in the future. We want it to be easy to understand, communicating clearly with other developers. And we want it to be ready for change, without requiring a total rewrite. By the end of this session, you will understand preconditions, postconditions, and how to write specs in TypeDoc that make your code robust against errors. Best way to think about a specification is a legal contract. In this relationship, the implementer, or the person writing the code, is responsible for meeting the contract requirements. The client, or the person calling the function, can rely on that contract, but also has a responsibility to meet any preconditions. Specifications aren't just one-sided. They place demands on both parties to ensure the system works as intended. This leads us to the concept of behavioral equivalence. As engineers, we often need to know, can we substitute one implementation for another without breaking the system? Behavioral equivalence is ultimately in the eye of the beholder, or rather, the client. Whether two pieces of code are the same depends entirely on what the client expects and what the specification promises. Let's look at a concrete example with a find function. Suppose implementation 1 searches from the start of an array and returns the lowest index. Implementation 2 is cleverer and searches for both ends at once to save time. If the value appears multiple times, these implementations will return different indices. Are they equivalent? Only if the client promises to pass an array where the value occurs exactly once. To make those implementations equivalent, we need a precise spec like the one shown here. It includes a requires clause, the precondition stating the value must occur exactly once. It also includes an effects clause, the postcondition stating it returns that specific index. Notice that the spec only describes behavior for legal calls. It doesn't need to specify what happens if the client violates the precondition. The reason that we do this is because it prevents the nastiest bugs, which usually happen due to misunderstandings at the interface between two pieces of code. When you have a precise spec, you can apportion blame. If the code crashes, you look at the spec. Did the client provide bad input, or did the implementer provide a bad result? This avoids team conflicts and helps you find the actual source of the error quickly. Think of the specification as a label on a black box. As a client, you shouldn't have to read 500 lines of complex code just to use a function. You read the spec, understand the what, and ignore the how. This is vital because implementations are often far more complex than their descriptions. This creates what we call the specification firewall. The firewall shields the client from the inner workings of the module, and it shields the implementer from needing to know exactly how every client intends to use their code. This separation of concerns is the basis for modularity in large systems. The byproduct of this firewall is decoupling, because the client and implementer are only talking to the spec. They can change their code independently, as long as they both still respect the contract. This gives the implementer the freedom to optimize the code or change the algorithm entirely without needing to notify a single client. Abstractly, a spec has a function signature, a requires clause, precondition, and an effects clause. The precondition is the client's obligation, while TypeScript can check the number and types of parameters. The requires clause handles logic that types can't easily express, like this number must be positive. The postcondition is the implementer's promise. It describes how the return value relates to the inputs, which exceptions might be thrown, and whether any objects are mutated. TypeScript checks the return type, but the human-readable effects clause defines the actual logical behavior. Mathematically, a spec is a logical implication. It is an if-then statement. If the precondition holds when the function is called, then the postcondition must hold when it finishes. The postcondition is essentially a guarantee on the state of the program after execution. But what if the client breaks the contract? If the precondition is violated, the implementer is not bound by the postcondition. The code is legally allowed to do anything: return garbage, throw an error, or enter an infinite loop. The client has no right to expect stability if they didn't meet their part of the deal. In TypeScript, we use a mix of tools. The static types are machine-checked parts of the spec that the compiler enforces automatically. However, the complex logic, or the requires and effects clauses, live in comments for humans to check and verify. The industry standard for these comments is the typedoc format. These comments start with /** and are placed directly before the function. This isn't just for show. Tools like VS Code use these to provide tooltips and can even generate full HTML documentation for your project. In typedoc, we use specific tags. The @param tag describes the parameters and their preconditions. The @returns tag describes the postconditions of the result. By standardizing this, we make the firewall clear and machine-readable for our development environment. Here is a typedoc spec in action for our find function. Notice how it clearly identifies the array to search and the value to look for, while explicitly stating the precondition and the value must occur exactly once. This renders into a clean interface that any developer can understand without looking at the implementation. Now let's talk about the golden rule of specification writing. Hide the implementation. A good spec should never mention local variables, private fields, or internal helper functions defined inside the function body. As far as the client is concerned, the implementation is invisible. It is behind the firewall. This is vital because the typedoc tool often extracts only the comments and renders them as HTML. So the reader might not even have access to your source code. Moving on to a major source of headaches in programming: null values. In many languages, any variable can be null, meaning it doesn't point to an object at all. This creates a massive hole in the type system because null isn't a true string or array. If you try to call a method like .length on it, your program will throw a type error or crash. Our core safety rule is simple. Avoid null. It is unpleasantly ambiguous and causes a staggering variety of bugs. In this course, we enforce this through a strict convention. Every function has an implicit precondition that all parameters and collection elements, like the items inside an array, are non-null. Similarly, every function has an implicit postcondition that it will never return a null value unless the specification explicitly says it might. We don't just ask you to be careful, we use strict null checking in our Typescript configuration. The compiler will actually flag it as an error if you try to assign null to a standard type like string. If you absolutely need a null value for some reason, you must explicitly declare it using a union type, such as string or null. But you should do this very sparingly. It is also critical that you distinguish between null and emptiness. An empty string literal or an empty array are valid, existing objects that you can safely call methods on. Because they are valid objects, our convention is that empty values are always allowed as parameters or return values unless your spec explicitly forbids them. Now let's pivot to testing and specifications. We often distinguish between black box tests, chosen based only on the spec, and glass box tests, which are written with knowledge of the implementation. But here is the golden rule. All tests must follow the specification. Even if you know how the code works inside, your test case must behave like a legal client and obey the contract. This means you must be careful not to test too much. If a specification says it returns an index of a value but doesn't specify which one when there are multiples, your test cannot assume it will return the lowest index, even if your current implementation happens to do that. If you assert a specific index that the spec didn't promise, your test is illegal and will break if the implementation changes. We also use specs to define the boundaries for unit versus integration testing. Unit testing focuses on the module in isolation against its specific spec. A test for function A should not fail just because function B, which A happens to call, is broken. Integration testing, on the other hand, ensures that these different modules have compatible specifications and are passing data correctly between each other. One final note on testing. Do not test precondition violations. Since the spec says the behavior is undefined, if a precondition is broken, you cannot check if a function fails fast or returns garbage. If you want to require that a function handles bad input by throwing an error, you must move that requirement from the precondition into the postcondition. Now let's look at mutating functions. When a function changes an object, these side effects must be explicitly described in the postcondition. Our implicit rule is the opposite of the null rule. Mutation is disallowed unless the spec says otherwise. If you write a sort function that modifies an input array, you must state that it modifies the array in the effects clause. In TypeDoc, you should document these changes in the @parameter clause. For example, you might write @param array, the array to sort, modified in place. This ensures the client knows their data will be changed when they call your function. Next, we have exceptions. Since an exception is a possible output, it must be documented in the postcondition using the @throws tag. However, we use exceptions for two very different reasons: signaling bugs and signaling anticipated failures. Exceptions for signaling bugs like index error or type error indicate that someone, either the client or implementer, has made a mistake, because these represent a failure of the contract itself. They are not part of the postcondition and should not be included in your @throws documentation. However, in contrast, exceptions for anticipated failures are for things the caller should expect and handle, such as a file not being found or a number not being a perfect square. These must be documented in your spec because they are a formal part of the interface that the client needs to be prepared for, even something like dividing by 0. Because TypeScript doesn't statically check exceptions, a safer alternative for special results is using union types. Instead of throwing an error, you can return number or undefined using the pipe operator. While we avoid null, we use undefined by convention to mean no value here at all. This is powerful because strict null checking enforces the client to handle that undefined case. If a client tries to perform math on a result that might be undefined, the compiler will throw a static error. The client must explicitly check the result before using it. If a client knows that a special result should be impossible in a specific context, meaning it would indicate a bug, they can use an assertion or the nullish coalescing operator to strip the undefined away. This asserts the value is present and lets the rest of the code treat the variable as a simple number. Finally, let's look at modules. In TypeScript, each file is a module. We use the export keyword to define which functions are part of the module's public specification. Anything not exported is private to the implementation. Clients cannot see it, and therefore it is not part of the contract. To summarize, specifications are the backbone of our goals. They keep us safe from bugs by documenting assumptions. They make code easy to understand by acting as a simple label on a complex box. And they make us ready for change by decoupling the client from the implementation. That wraps up our deep dive into specifications. Remember, a good spec is a firewall that gives you the freedom to improve your code while giving your teammates the confidence to use it. Happy coding!